Okay, so today we are continuing on the same section. So this is again section 6.4. This is day 2. We'll also do a third day on it tomorrow when we talk about trig proofs. So today we're going to talk about simplifying trig expressions. And so what we're going to be looking at now is something that we talked about yesterday. We looked at sine theta plus 1 over cosine theta yesterday. And to add those together, to simplify this, we have to get a common denominator, which was what?
That would be
cosine of theta, right? So this was cosine of theta. This was cosine of theta. This was already over cosine theta, so that didn't change. This became sine theta, cosine theta, which then became sine theta, cosine theta, plus 1 over cosine theta, right? So that's a very simplistic example of one of these simplifying trig expression problems. Now let's take a look at a slightly more complex one. So again, this is the one that was in your notes from yesterday. This is not new. So now what we're going to do is we're going to take a look at secant of a plus 1 over sine of a plus tangent of a. So the idea is that we need to simplify this thing down. Now, one of the things that you want to be on the lookout for is stuff like sine squared and cosine squared, because we can use our Pythagorean identity, which is what that sine squared plus cosine squared equals 1 from the box is actually called. And we'll talk more about those identities as we go on. But what I really want you guys to be on the lookout for here is functions like tangent, cotangent, secant, cosecant. Typically what you're going to want to do on these is you're going to want to convert them into sine and cosine. And so I want to talk to you guys about that a little bit before we get started. So we know that secant of theta is 1 over cosine of theta. And we know that cosecant of theta is what? 1 over sine of theta, right? Those are reciprocals of each other. Okay, that we've already talked about. What we have not really talked about is tangent and cotangent very much. Remember, the tangent, guys, is your y-coordinate divided by your x-coordinate. But what is your y-coordinate in terms of trig functions? Sine. So this is really sine theta over, what is the x-coordinate? Cosine theta. And so another identity that we have is that tangent of theta is really sine theta over cosine theta. Likewise, what is cotangent going to be? Cosine theta over sine theta. It's the reciprocal of tangent. So those are two new identities, and these are the identities that we're going to use to get these problems started. So what we're going to do is we're going to take secant of a and change it into what? 1 over cosine of a. And you do have to use the correct letter, guys. Don't make it theta if it's an a. Don't make it an a if it's an alpha. You have to use the proper letter. So that's our secant of a plus 1 over sine of a, which is already in terms of sine and or cosine, plus tangent, which is really what? Sine over cosine. So sine of a over cosine of a. Does everybody see what I did? So I just converted my other trig functions into sine and cosine. Now I have nothing but sine, cosine, and numbers left. Yeah, we're going to have to do that in just a moment. So notice that what we have is we have a complex fraction, right? We have a fraction. Actually, we have a couple of fractions inside of a fraction. So what you're going to want to do is you're going to want to work with the numerator first. So what I would do is I would go off to the side somewhere and say, okay, 1 over cosine of a plus 1 is really plus 1 over 1. What do we have to get to add those together and make them into one fraction? Common denominator, which is going to be cosine of a. This is already over cosine of a. This becomes cosine over cosine, which makes this 1 plus cosine of a over cosine of a. Is everybody with me? That's the numerator. So now that's what I have on the top. 1 plus cosine of a over cosine of A. Divided by, and make the main fraction bar longer so it stands out. If you make them all the same length, then you're going to kind of get lost as to where that main division bar is. Now we're going to do the same thing with the denominator. The denominator is sine A plus sine A over cosine of A. We have to get a common denominator, which is going to be what? Cosine of A. This was already over cosine, so the top stays sine. What does this one become? Yeah, sine A cosine of A or cosine of A sine of A, whichever you prefer. And then when you put that together, you get sine of A cosine of A plus sine of A over cosine of A. Now it's all one fraction. That's your denominator. Anything hard about doing either one of those by itself? So just work with one at a time. Don't try and work with the whole fraction at once. Now, we don't divide by fractions. What do? Multiply by the reciprocal. Is everybody okay if I erase this work? Just so I have room? No? Okay, let me erase this then. Let me take this and move it up to the top. So those of you that are still copying it can copy it. How's that? So now what we have is we have 1 plus cosine of A over cosine of A, that's the numerator, times the reciprocal of the denominator. Cosine A over sine A, cosine of A, plus sine of A. What's that? Somewhat. Okay, what happens now? The cosines cancel out, and so we end up with 1 plus cosine of A over sine of A, cosine of A, plus sine of A. Now we're not done, but is everybody with me up to this point? Do you guys see what we can do with the denominator? Take out a sine of A. Very good. So the top becomes 1 plus cosine of A still. The bottom becomes sine of A times what? Cosine of A plus 1. Does anything cancel now? Yeah, what cancels? But they don't match, do they? They do because it's what? Because it's plus. If it was subtraction, would they be the same? No, we talked about that yesterday. What would we have to do to make them cancel? Take a negative 1 out of one or the other. And again, I would take it out of the top just to make life easy. But now this cancels this. What does that leave us?
1 over sine of A.
1 over sine of A. Is there another way to write that?
It is the
cosecant of A. So, very good, cosecant of A. Now, everybody see that? Now, does it matter which of those two answers you write? The answer is no. I will accept either one. The reason they are interchangeable, guys, is this, and this is very important. I don't care which answer you write because they both use the same number of trig functions. There's one trig function here, there's one trig function there. But if you got an answer like sine of A over cosine of A, you need to simplify that down to what?
sine.
If it was sine over cosine, what would it become? Tangent. You need to simplify it down to tangent because now tangent is one trig function, sine over cosine is two trig functions. One trig function is simpler than two trig functions. But because these both just use one trig function, they're equally as simple. So either one of these answers is fine. Where were you coming from? You went to. Okay. Thank you. All right, guys. Questions about that example? Let's take a look at another one. So notice, guys, that we ended up with this complex fraction. So we worked with just the top, the numerator, made it into one fraction. We worked with just the bottom, the denominator, made it into one fraction, and then we multiplied the top by the reciprocal of the bottom, and then we started factoring and canceling. Okay? This is what you're going to see on probably 90% of these problems. Because remember, anytime you see a fraction in the original, if that fraction has secant, cosecant, tangent, cotangent in it, guaranteed you now have complex fractions. You have fractions inside of fractions. So you're going to see this constantly. So don't try and work with the whole thing all at one time. That's the mistake that most people make. If you work with just the top and just the bottom, then put the two together, it makes life so much easier. Questions about that? Okay. Let's take a look at this one. Let's look at sine of A over cosine of A plus cosine A over sine A. And we want to simplify. Well, in order to simplify, what are we going to have to get here? Common denominator, which is going to be what? Cosine A sine A, right? So I multiplied the bottom by what to change it from cosine to cosine sine? So we multiplied top and bottom by sine of A. So that becomes what on the top end? Good. Sine squared A. What do I multiply top and bottom by here? Cosine of A, which makes the top what? Cosine squared A. Now I put those together into sine squared A plus cosine, sorry, tablet's not cooperating, cosine squared A over cosine of A sine of A. Everybody with me so far? What happens to the top now?
That's going to equal 1.
Becomes 1. Very good. Remember that last entry from the box, guys. Cosine squared plus sine squared equals 1. So this becomes 1 over cosine of A times sine of A. Now, there is actually another way you can write this. Let me show you the other way. It is not better. It is equally the same because it will still involve two trig functions. But I want to show it to you because it may pop up when we do trig proofs where they tell you what you're aiming for. Okay? So, here's the deal, guys. Do you see that this is really 1 over cosine of A times 1 over sine of A? Isn't that the same thing? What is 1 over cosine of A? Secant of A. What is 1 over sine of A? Cosecant of A. So this would be another answer that is acceptable. But do you see that they both use two trig functions? So one is not better than the other. You could stop at the first one, but I'm showing it to you. I would personally stop right here. Probably. I might go to that, but let's just say we stop right here. This is perfectly fine, guys, but you need to understand that this can be changed into this, because when we do trig proofs, they may ask you to prove that this is equal to this, in which case you have to go all the way to the end. Okay, all trig proofs is what we're doing right here, except they tell you where to stop. They tell you what you're aiming for. Okay, so in a way, the trig proofs are actually easier than these problems because you can kind of look and see what you're headed towards, whereas these you're kind of just shooting in the dark and seeing what you can do. Okay, the trig proofs give you a little more direction. Any questions about how that works? And it's just going to take some practice. Be on the lookout for things that factor so that you can cancel factors out. Okay? Be on the lookout for things that change into terms of sine and cosine, like secant, cosecant, tangent, cotangent. Be on the lookout for complex fractions that you have to simplify. Those are the recurring items that you're going to see pop up over and over and over again. Okay, the other thing that I want to talk to you guys about very briefly is I want to talk to you guys about problems like this. So they may give you something like, given that sine of theta equals 2/3, and they tell us that theta is between pi over 2 and pi. They want you to find cosine of theta and, let's say, tangent of theta. So this is example 6. Now they could ask you to find all 5 of the other trig functions, or they could ask you for just a couple of them. And this one they're asking us just for a couple of them, 2 of them. So do you guys see that this is really the same kind of problem we saw in the first section, where they gave you point P and they told you that the y-coordinate was 2/3 and that it was in quadrant 2, and they asked you to find the x-coordinate, and then they asked you to find cosine or tangent, things like that. So we've actually done these kind of problems before. There are 2 ways that I want to show you to do this. And I don't care which way you use at this point, but I want you to see the other way because the other way becomes very useful on other similar problems. The way we've been doing it is sine is really what coordinate? That's the y-coordinate, right? So we could just use x squared plus y squared equals 1. So we would get, sorry guys, let me start this tablet over again and reset it. So just take a moment. All right. So that would give us x squared plus 2/3 squared equals 1. That's x squared plus, what's 2/3 squared? So x squared is equal to 1 minus 4 over 9. Right? That's really 9 over 9 minus 4 over 9, which is what? Well, it's 5 over 9. That's x squared. So now when we square root both sides, we get x equals plus or minus the square root of 5 over 3. Question is, should it be positive or negative? Well, this is quadrant 2. So should x be positive or negative? Negative. So that means that this is our y-coordinate. 2/3. Our x-coordinate is negative rad 5 over 3. Can we now find cosine of theta? What is it? Right, the x-coordinate. How do we find tangent? Exactly. 2/3 y divided by negative rad 5 over 3, which is x, but we don't divide with fractions. Multiply by the reciprocal. Very good. So that's going to be 2 over negative rad 5, which is going to become negative 2 rad 5 over 5 is correct. So do you guys see how those work? That's one way to do the problem. Now another way to do it is instead of using x squared plus y squared equals 1, we can use cosine squared plus sine squared equals 1, in which case we would have just gotten cosine equals negative rad 5 over 3 instead of x. But it's the same thing, right? Let me show you another way to do these, though. And I don't care which method you use at this point, but I want you to see this method because it is useful on some of these problems. Very useful. Another way to do this problem... Actually, let's do it this way. Another way to do this problem is to say, okay, we're between pi over 2 and pi. So that's quadrant 2. So we have our terminal side of our angle in here somewhere, right? We're going to drop a perpendicular to the x-axis. Remember, it's always x, never y. Why is it always x and not y? Are things based on what?
The unit circle is based on 0.
Yeah, where 0 is. Where's 0? X, the x-axis. So that's why it's relative to the x-axis. Okay. So we know that sine of theta is equal to 2/3. Sine is equal to what over what in words, in terms of sides of a right triangle? Opposite over hypotenuse. So another way to do this, guys, is to label, so our theta is technically out here, right? But as long as we adjust positives and negatives for the quadrant we're in, we're allowed to treat theta as if it was here. The opposite side would be 2, the hypotenuse would be 3. Can we now find the missing side? By using what? Pythagorean theorem. So 2 squared plus x squared equals 3 squared. So x squared is equal to, that's 9 minus 4 is 5, so x is equal to plus or minus the square root of 5, right? Now, we're in quadrant 2. Should x be positive or negative? Negative. So this is negative square root of 5. So do you see how we get this picture, guys? We get a right triangle. We use the Pythagorean theorem. Make sure that you have adjusted for any negatives. The x can be positive or negative. The y can be positive or negative. The hypotenuse can never be negative. The hypotenuse is not referring to the coordinates of a point. What the negative rad 5 and the 2 are, guys, are the coordinates of that point. Negative rad 5, comma 2. Do you see that? The 3 is not an x or a y coordinate. So the 3 is never negative. It's only a length. So any negatives have to be attached to the x and the y only. Everybody see that?
How would the x be positive in that kind of situation?
Well, it can't in that quadrant, but it could be over here or it could be over here in a different quadrant. All right? So you just have to look at the quadrant. So now to find cosine of theta, cosine is equal to what over what in terms of size of the triangle? Adjacent over hypotenuse. Adjacent over hypotenuse. Tangent of theta is equal to what over what in terms of the right triangle? Opposite over adjacent, which becomes negative 2 rad 5 over 5. Do you guys see we get the same two answers we got the other way? But a lot quicker, in my opinion. And also, this method makes life a whole lot easier when we get to other types of problems that are along the same lines, but not quite the same. You'll see what I mean later on. Okay? Not today, but another day. So I want you to see both methods. For tonight, I don't care which method you use. I just want you to see both of them. I personally prefer the triangle method. But if you prefer the previous method, like we did in the first section, by all means go ahead and use it. It gave us the same answers. It's not a problem. Now, what happens if instead of sine, they give you secant is rad 5 over 7? Actually, rad 5 over 2. How would we do this then?
You have to
yeah.
take it into a...
This means that cosine is really what? 2 over rad 5, which is 2 rad 5 over 5, right? And then you could say, okay, well, that's our x value, and then do x squared plus y squared equals 1. Okay? But here's the issue, guys. What happens if what they give you... What happens if what they give you is tangent of theta equals square root of 3 over 3? Which coordinate is that? It's y over x. But does that mean that this is the y coordinate and that's the x coordinate? Well, you can't plug those into x squared plus y squared equals 1. Those are already bigger than 1 by themselves. So now you won't be able to do that. But with the other method, let's say you're in quadrant 1, and that's theta. Tangent is opposite over adjacent. I can put the square root of 3 there and the 3 there, and I can find this with the Pythagorean theorem, and then I can do it with that triangle method with no trouble. So this is, again, guys, why I prefer the triangle method, because it makes life so much easier on a variety of problems. So keep that in mind when you're doing these, okay? So if they were asking us for, let's say, sine of theta, so this would be 3 squared is 9, so this would be the square root of 12, which is 2 rad 3. So when you do sine of theta, it's going to be opposite over hypotenuse, which cancels and gives you 1/2. Right, because now you're just using SOHCAHTOA to finish these. Does that make sense? Questions about that? So that's why, do you guys see why I prefer that method? It's much more versatile than the other method, than the book's method for doing these. Okay. Questions about anything?
How do you know which one is, like, what quadrant?
This is what told us what quadrant. Right? Pi over 2 is here. Pi is here. So that means we're in quadrant 2. Okay.